Now we're ready to talk about really what is analytic combinatorics. So it's a calculus for the quantitative study of large combinatorial structures. And generating functions are the central object of study in analytic combinatorics. So the basic process is a three-step, pretty simple. First thing we do is define what's called a combinatorial construction that precisely specifies the structure that you want to study. The second thing we do is use what's called a transfer theorem, a symbolic transfer theorem, to get a generating function equation. And then we use another analytic transfer theorem to extract the asymptotics of the coefficients. That's it, a three-step process. And what's important is that it's very often the case that all three steps are almost immediate. For example, for our binary tree question, how many binary trees are there within nodes? With analytic combinatorics, we write down a combinatorial construction, that's a formula like that one, and I'll talk on the next slide where that comes from. Then we use a transfer theorem, this one's simple to prove and simple to apply, that immediately gives a generating function equation. It's the same one that we got the hard way before. And then we use an analytic transfer theorem that immediately gives us the coefficient asymptotics. And again, this theorem is very sophisticated to prove, but it's easy to apply. So three-step process to solve the same problem, avoiding all of the detail. That's what analytic combinatorics can do for us. Let's look at these three steps in detail. So the first step is to specify the class using a combinatorial construction. And these things are built from natural operations. And once you see a few of these in simple examples, you'll see how natural they are. They're algebraic formulas that are built with combinatorial operators. And the operands are either atoms or the basic building blocks like nodes in the binary tree, or they could be other constructions or classes. And there's two cases that I won't get into that much detail on in this talk, but either the atoms are unlabeled, there are no difference between them, or they're all different, they're labeled. And that leads to differences in the operators. And in the unlabeled case, we use ordinary generating functions. In the label, we use exponential. But at this level, there's not much difference. And the idea is that what we're doing is very similar to formal languages in computer science, but the idea of the combinatorial construction, we are particularly paying particular attention to ambiguity, if you're familiar with formal languages. And so there's a lot of constructions, but the basic ones that I can use to illustrate what analytic combinatorics is are very simple. So there's a union operation, so A equals B plus C. And the letters just represent classes of combinatorial objects. A combinatorial class is a set of objects and a size function is all. There's a Cartesian product, which is pairs. And there's sequence, which is a sequence of just shorthand for pairs, any number of pairs. So those are the basic constructions that we can use. And for example, this is just a fully formal basis for being able to write down a specification of what is a binary tree with that formula. T equals E, which is the empty class, plus Z, which is a class containing one thing, which is a node. That is a product with a node. A tree is a sequence of a node and two trees. So that's a formula that fully specifies what we mean by binary tree. And we define a binary tree in English. We usually say a binary tree is empty or a node and two binary trees. This is saying that formally in math speak. That's what a combinatorial construction is. And we'll see lots of examples of combinatorial constructions later on. So then the next thing is to introduce generating functions. Well, one of the things about the combinatorial constructions that we use is that we associate the constructions with operations on generating functions. So this part happens immediately. So for unlabeled classes, we use ordinary generating functions, and it's the same as before. We sum for all sizes the number of objects of a given size times z to the n, where z is a synthetic variable. And by the way, that's exactly equal to summing over every tree z to its size. Because for all the trees of size n, there's one term, and that gives t sub n. And that representation of the generating function is what gives easy proofs of the transfer theorems, although I won't take time to do the proofs right now. So the basic transfer theorems are very simple. If you've got two classes B and C and you take the union, the generating function for the result is the sum of the generating functions of the two operands. If you do the Cartesian product, it's the product. And if you do the sequence of, it's 1 over 1 minus. And that just comes from sum of 1 plus b of z plus b of z squared plus b of z cubed and so forth. That's easy to prove from the product. So given the operations, we immediately have a translation to generating functions. So for example, for binary trees, our combinatorial class is the set of all trees, and the size function is the absolute of t notation is the number of nodes in t. So what we're interested in is the counting sequence, the number of trees with n nodes. And from this very basic information, we have the construction that I showed on the last slide immediately translates to a generating function equation. The empty class generating function for that is 1. Z, the generating function for a class consisting of a single node, is just z. And then there's t of z twice, so it's z times t of z squared. So that's a fully rigorous mathematical transfer from a construction to a GF equation. We have many other constructions, but for all of them there's associated transfer theorems. Nowadays that's what we mean by a combinatorial construction. That's one for which we know a good transfer theorem. So generating functions are the key to analytic combinatorics. But I have to point out quickly that the use of generating functions in combinatorics was very controversial for some time. For example, here's a quote from Claude Berger, a French mathematician, and expresses the point of view of many people working in combinatorial mathematics. It says, a property is understood better when one constructs a bijection than when one calculates the coefficients of a polynomial whose variables have no particular meaning. The method of generating functions, which has had devastating effects for a century, has fallen into obsolescence for this reason. That was Berger's point of view. Philippe had a completely different point of view. He says that they are really the central objects of the theory, not a mere artifact to solve recurrences, as is still often believed. And we'll see why when we get to the next step of analytic combinatorics. What we're going to do is view the generating function. It's still a synthetic variable, but we're going to view it as a complex variable. So the generating function is going to be a function in the complex plane. And that viewpoint allows us to unlock analytic transfer theorems that immediately give us the coefficient asymptotics. For example, even in real analysis, but also in complex analysis, the coefficient of z to the n in 1 over 1 minus z over rho, so that's got a pole at rho, it's rho to the minus n. Sum of z to the n, rho to the minus n. So that's easy. But we can do much, much more. For example, if we take 1 minus z over rho to the alpha, where alpha is any real, except it can't be a negative integer, degenerates in that case. It's asymptotic to n to the alpha minus 1 over gamma alpha. That's the gamma function which generalizes the factorial, rho to the minus n. And even if there are logarithmic factors, we can prove the transfer theorem that coefficient of z to the n and that function throws out a log n factor. Now these are simple to apply. They couldn't look simpler. The proof of them is extremely sophisticated, and really was a publication of this paper by Philippe and Andrew Odlyzko in 1990 was really a watershed moment. Before that time, we suspected that we could get these answers out in this way, but proving it was another thing entirely. That's what I said when I said we needed to do the math, and Philippe and Andrew Odlyzko definitely did the math. It's worth understanding this paper, but it's truly a tour de force and a masterpiece that now we can benefit from. There's a very long list of transfer theorems of this type, really starting with this basic one. And these things are effective even for approximations near the singularities when there's other functions involved. But for example, for our problem, if you want the coefficient of z to the n in square root of 1 minus 4z, you just plug in the standard scale equation, alpha equals minus 1/2, and rho equals 1/4, and immediately you get the asymptotics of the coefficient. It's asymptotic to n to the minus 3/2 over gamma of minus 1/2, 4 to the n. And gamma of minus 1/2 is minus 1/2 square root of pi, and that, boom, that gives us the asymptotics immediately, just directly applying the theorem without worrying about all the sophistication underlying its proof. So that's the third step. So there you are. That's two different ways to count binary trees. You can go through the classical analysis of algorithms, all those steps, which, by the way, a lot of students, and I'd say even a lot of professors, might take quite a while to really get through all those steps to do this Catalan number derivation. But with analytic combinatorics, it's boom, boom, boom. There's the answer, 4 to the n over square root of pi n cubed. Take your pick. Most modern researchers who are looking at scientific study of large quantitative structures are going the analytic combinatorics way. Because it's effective for a very broad variety of combinatorial structures. For example, the unlabeled case that we're talking about. So we talked about trees. There's other types of trees. I'll talk about that in a minute. It works for strings, or even just for properties of numbers. For compositions, those are sets of numbers that sum to n, or partitions where you don't take the order into account. Or for languages, for regular languages or context-free languages, are just examples of combinatorial structures that we can specify, and therefore we can analyze with analytic combinatorics. Labeled objects are things like permutations, or balls and urns, or cyclic permutations, or functions, we call words, functions from one finite domain to another. Labeled trees, those are acyclic mappings, or general mappings, and many, many others. These are just the basic ones. And not only that, analytic combinatorics is fully extendable. So new constructions are easy to derive. Just use the tools the way you would for any formal language. And not only that, if you don't find a construction that you need, you can develop a new one and a corresponding transfer theorem. And that's happening regularly for all sorts of applications. So just to look at some elementary examples briefly, you can see how over and over again we can just go from a construction to a generating function equation to get the coefficients out. Sometimes the transfer theorems are very simple. They're just Taylor series expansions. So an integer is just a sequence of unmarked objects, a positive integer, say. So that's z cross sequence of z. So that immediately translates to z over 1 minus z, and the number of integers of size n is just 1 for n bigger than 0. And then we can use build on that construction to talk about partitions and compositions and other things. Or strings, so say a genomic string, it's a 4-character string. It's a sequence of 4 different atoms, or in this case, say m different atoms. But that immediately gives strings from an alphabet of size m. The generating function is 1 over 1 minus mz, and there's m to the n of them. Again, very fundamental construction. Binary trees is the one that we just did that needs an analytic transfer theorem. Now below the line is the labeled universe. A permutation is a sequence of labeled objects. The multiply operation involves relabeling, and I won't get into that now, just to show what the constructions look like. And it's exponential generating functions, so we need to multiply the coefficients by n factorial. Cycles are labeled cycles. It's log of 1 over 1 minus, and immediately gives out the generating function. Words is a if you specify the indices that have each value, it's a sequence of sets, and so immediately the transfer theorem gives e to the mz, and it's m to the n. It's just looking at the same combinatorial objects in 2 different ways. But there's all sorts of benefits to doing that, because one of the real sweet spots of analytic combinatorics, and one of the reasons it's so successful, is you take those fundamental constructions and transfers that are easy to understand, and once you do it, then you can have variations and get the analysis immediately. So we talked about binary trees, but you could do ternary trees, or ordered trees where every node can have any number of children at all. Or you can specify that the number of children has to be less than a given value, say 0, 1, or 2, say. Or you can have actually arbitrary restrictions of any kind. Or it's got to be more than 2, and there's important applications of every one of these. They're all easily handled with symbolic transfer theorems. Now, sometimes we can get to generating function equations that seem difficult to deal with. A 5-way tree is going to have a 5th order polynomial and so forth that we might have to work with. And that's might seem challenging, but actually another hallmark of analytic combinatorics is that a lot of times a single transfer theorem can cover a broad variety of cases. And those are called universal laws that are extremely general. Now, that's one of the hallmarks of analytic combinatorics. For example, context-free constructions. So this is when we can have a whole system of combinatorial constructions where the operators is one of the simple ones that I've talked about. Those with the symbolic transfer go immediately into a system of generating function equations. You're going to write those out symbolically. They can be pretty complicated. But with Grosvenor basis elimination, for whatever it is, it can be reduced down to a single generating function equation. Now, there's certain technical conditions to make all this work. I don't want to oversimplify it. But in the end, what happens is then that single generating function equation, there's a theorem called the Drumoto-Lally-Woods theorem that takes that down to an explicit solution. So for any system of combinatorial constructions, it's always going to have a solution of this type with C, A, and B constants that we can compute, or we can get more asymptotic accuracy if we want. So the analytic transfer theorem from singularity analysis that we just did gives this simple asymptotic form. You have a context-free construction, it's going to be A over 2 square root of pi n cubed B to the n, where A and B are constants that we can compute. It's amazingly general universal law, and there's several universal laws that we know. Before analytic combinatorics, you would find papers, long papers that use the old methods to come out with the results, and it was becoming pretty clear to experts that there had to be something behind square root of pi n cubed appearing in the denominator all the time. But we can now know that why that happens, because we have the universal laws. And again, there's several others, and one of the goals of modern research in analytic combinatorics is discover more and more universal laws. So that leads me just to briefly describe analytic combinatorics at the next level, beyond what I've been able to talk about right now. One thing is that actually often what we want is multivariate generating functions to handle combinatorial parameters. Multivariate analytic combinatorics sometimes will give us limit laws about the values of parameters. A lot of time the behavior of the functions in the complex plane is very complicated, and we get oscillations. And like that formula that we had involving the gamma and zeta function is an example of that. So the answer is not simple. We have to deal with that. Sometimes there's a method known as saddle point asymptotics that we have to use for generating functions that don't have singularities. You can do more than just figure out a counting sequence from knowing an equation that the generating function must satisfy. One of the things you can do is generate random structures. And one of the important applications of analytic combinatorics is use combinatorial constructions as a basis for generating big random structures, which you can compare against real data to decide if you have a decent model. As I mentioned, and I didn't discuss in detail, the analytic transfer theorems sometimes have technical conditions that need to be checked, and sometimes that's really the burden of completely solving the problem. And so we want to remove as many such conditions as possible. And the other thing is another thing is when we get into analysis of algorithms, we're often talking about, with programs, transforming data from one combinatorial structure to another, which is a complex process that's difficult to capture, maybe even with analytic combinatorics. And then also we easily can specify constructions that lead to relatively complicated implicit functional equations that are not so easy to handle with analytic transfer theorems. But still, there's a very broad variety of problems that can be handled simply with combinatorial constructions, transferring immediately to generating function equations, and then translating to coefficient asymptotics one step after another. For example, that's partitions. How many ways are there to write an integer as a sum of other integers, of smaller integers? So combinatorial construction for that is multiset, and the transfer theorem immediately gives the generating function, whatever 1 minus c, and so forth. And then there's an analytic transfer theorem that immediately gives the coefficient, the asymptotics. So just another example, series parallel networks, or this is a model for Boolean expressions in electric circuits and many other things. And so you want to know how many of those are, how many bits would you need to represent one, or study some parameter of it. You can use a simple combinatorial construction, get a simple generating function equation that is amenable to the standard transfer theorem, where the exponent is 1 over 3 minus square root of 8. Relatively straightforward to study such problems with analytic combinatorics. So surjections, that's the number of mappings onto initial sequence of the integers, and that's got lots of applications. And again, it's a sequence of a set, immediately gives the generating function, and then it's 1 over 2 minus e to the z, so the singularities are at 2 over log 2, and at log 2, and so that gives the asymptotics immediately. components in mappings. So a mapping is a function from the integers 1 through n to itself, and that gives it's done with two constructions. It's a cycle of trees, really. And a tree is a node and a set of trees. So that's what those constructions say, and they immediately translate into those generating function equations, and then we have transfer theorems that immediately give the coefficient asymptotics. So there's a very, very long list of standard combinatorial objects and combinatorial parameters that are classical objects that are amenable to study with analytic combinatorics. And then all kinds of new objects that were too complicated to deal with using classical techniques that people have studied and learned properties of with analytic combinatorics. If you can specify it, you can analyze it. So that's what's in our 2009 book. This is an overview of what's inside and how it's related and what comes out. So the first thing is the symbolic methods, the symbolic transfer theorems for labeled objects, unlabeled objects, and parameters corresponding to ordinary exponential and multivariate generating functions. From those symbolic methods, you can either go into complex asymptotics to go ahead and get out the asymptotic counting results, as I've discussed, but you can also get out moments of parameters as well. And you can get properties of random structures and limit laws as well. So that's, again, in the short lecture, best I can do to describe really what is analytic combinatorics. And so 2009, we think this one is solved. It's got all kinds of applications, from studying patterns in random strings with finite fields, standard algorithms like hashing, data compression, geometric search. Chemistry has combinatorics, and one of the original histories of our field was Polya, George Polya, studying applications in chemistry. There's a connection to analytic number theory. People are studying planar maps in graphs and probabilistic stream algorithms. We have a solution to a standard theorem in computer science that is based on analytic combinatorics. Bioinformatics is a very rich and fertile area of application, and statistical physics, and automatic testing of programs, and many, many others. If you can specify it, you can analyze it, and analytic combinatorics is here to stay. So I mentioned that it was 30 years in the making to get to the book, and I just want to finish by pointing out that we're still counting, though there's a second edition now of the original Analysis of Algorithms book that I did that includes an introduction to analytic combinatorics, and I know Philippe always wanted that. And more than that, there's extensive web content in the process of development, and also online courses. So it's a very active and vibrant field, and if you want to learn more about analytic combinatorics, there are many ways to do so. I've given a lecture like this many times since Philippe's death, and I at first ended with saying it was a pleasure to work with Philippe, but now I think it's better to say that it's a pleasure to be working with him, because I feel that I'm still working with Philippe, and I hope that many more of you have the opportunity to do so through the materials that I've discussed.